Okay, so after the big celebration of the armistice of the Second World War, I guess somehow, at least it's my case, somehow we left behind a little bit our mathematics, so I don't think it's too bad to recall a little bit the different kind of things we learned just before the celebration. Yes? Okay, so in principle, we start with a random vector whose dimension actually can be random. Usually we call it random vector capital L, but it's rather a so-called point process. So a branching random walk, usually the position is noted by v of x. Here, usually when we have a random process, the index is time, but here, the index here is a vertex in the genealogy tree. So I can write a generic picture about the position of branching random walk. So at the beginning, I have just one particle at the origin, let's say. So time is discrete. At time 1, so this guy is going to have some children, and the number of children is distributed as random variable, capital N. So if you choose capital N to be just fixed, then okay, let's say capital N is 2, then you always have 2 children. And the position is distributed as this random vector. So this psi 1, psi 2. Yes? So that's what happens at time 1. At time 2, both of them die, and each is going to give children, and the children of each are distributed according to the same distribution. So let's say this guy gives just 1 child, this guy gives maybe 3 child, and so on. Maybe this guy doesn't have child at all. This guy will have 2 children, 1, 2, and so on. Yes. So on the right, so this is the picture on the left-hand side gives you the position in space of the branch random walk. On the right side, I'm going to draw the genealogy tree. So at the beginning, I only have 1 particle starting from the beginning. At the first generation, I have 2 children. So I put these 2. In the second generation, so the first child has 1 child. So the first one just has 1 child. The second one has 1, 2, 3. So this guy has 3 child. And in the third generation, this first one has 2. So I hope my picture is correct. And among the 3 other, the first one doesn't have 1, so this guy stops here. This one has 1, just 1. So this has 1, and the last one has 2. So that's, and so on. Yes. So this is on this are called capital T. So the difference is that here you see where each particle is, whereas on the right-hand side we have just started. On the right-hand side, you don't see the position is in space. You only see the vertices. That's the only difference. Yes. But sometimes it helps to draw the genealogical tree.
And here, N capital is random.
In principle, capital N is random. Yes, but if you don't, well, actually, whether N is random or not, it doesn't change anything. So if you really feel annoyed by the randomness of capital N, all you need to do is just to tell yourself that, okay, I want to take capital N to be over 3. It doesn't make your life easier anyway. Okay, so that's what the basic definition, basic notation. And we have this very important assumption, which I will write it here, because we always assume this, which we call assumption star. Assume that if I sum over everybody in the first generation of e to the minus the position, assume that this expectation to be 1. This is only part of the assumption. So let me remind you that by definition, it's nothing but the expected value of the sum over everybody in the random vector capital L e to the minus psi I. It's identical, yes? But I prefer to write it in terms of the branch random walk instead of in terms of the random vector capital L. And the second part of the assumption is that you sum over the same particles, but you multiply e to the minus vx by vx, and assume that this is 0. Now, I think everybody understands why this assumption is good. So under the assumption star, we have 2 fundamental martingales. One of them, so I have martingales. Actually, there were others, but these 2 are the most immediate and the most useful martingales. The first one is so-called the additive martingales. So I sum everybody in the nth generation of e to the minus v of x. Actually, only the first part of the assumption is sufficient to ensure that this guy is a martingale. It's obvious. Okay? Okay, so this is the additive martingale, and the other one, which is maybe it doesn't look as nice as the first one, but actually it's more important, is the so-called derivative martingale, is v e to the minus vx. Now you need to have both identities in the assumption to make sure that this guy is also a martingale. Okay.
Are there any sense in this minus, which
Sorry?
is everywhere?
Oh, because I want to look at the minimum. Then everything in all the forthcoming theorems will be positive. Okay. If I take the positive, if I don't put the minus sign, then everything in my theorems will be negative, and I'm going to look at the maximum. So it depends on your choice.
If you just write the minimum, then you may not don't think whether it is positive or negative or whatever or not. Okay, I just mean that so far this minus is completely
arbitrary. I agree. Yes, yes. I think at the beginning everybody was working at the maximum because everybody was working on the first order theorems. For the first order ones, you don't see any difference between maximum and minimum. If you look at the second order, then you see that for maximum, actually, everything is slightly below the first order. Whereas for the minimum, everything is slightly above the first order. So personally, I find it more convenient to look at the minimum. But OK, I'm aware that many people still prefer to look at the maximum. So this is a non-negative martingale, so we know that it converges automatically. So in particular, this guy goes to 0, so which means that the v of x goes to infinite uniformly. So if I look at the minimum position in the nth generation, I know that it goes to infinite almost surely. Well, we need to be slightly more careful with about convergence, because according to our assumption, capital N in principle can be 0 with positive probability. So nothing guarantees that my system will go forever. So when I say almost sure, it's only on the set when the tree is infinite. Okay. So if the tree stops somewhere, then I'm not going to have any convergence, because I mean there will be no this guy when n is sufficiently big. Okay.
When mn tends to 0, we know that mn tends to somewhere, but why 0? Do you need any further assumptions to get it?
This goes, so it means that this, okay, every term, how would you say, each term must be 0, because if you add something, then, okay, I'm a little bit too quick, maybe, yes, I'm not quite sure. Okay, for the moment, I think, actually,
it is clear that mn tending to 0 implies the convergence of minima. It is,
yes.
It is clear.
Yes,
what
yes.
is not clear is why mn tends to 0.
That's true, because that's something which I stated, but which is not pronounced, which is not proved yet, and the proof will be not even next week, but the week after.
But just for now,
yes.
May we know whether you need for this some further assumptions or not?
I don't need any further assumption. Okay. That's the only thing you need to is this star.
Both parts of the star?
Yes.
Both?
I would think so, yes. Okay, so what's, okay, and the only quantitative tool I know for branching random walks is the many-to-one formula, which says that for whatever n, if I sum over everything in the nth generation, I take whatever measurable function of the branching random walk. So in this picture, let me sum over all the particles, all the vertices in the nth generation, let's say n. So I take one of them, let's say this x. Then I write there is a unique shortest path connecting x to the root. Then the root, I'm going to call it, well, x0, which doesn't matter, x1, x2, and so on, until xn, which is x itself. That's my notation. Okay, so these are all the ancestors of x in the past. Yes. So I look at a measurable function of not only of v of x, but even the whole history. Yes. It turns out that it's something very simple. It's the expected value of the same function g of s1, capital S1, capital S2 until capital Sn, but with a density which is exponential to the terminal value. Here, the capital S actually is sum of IID random variables, so it's so-called random walks. Okay, S0 is supposed to be 0. Okay, so on the right-hand side, I really have a random walk. I need to tell you the law of this new random walk. So I take expected value of whatever measurable function, let's say non-negative, S1. All I need to do is just to take n to be 1, and then I take this one to be h of S1. So that's equivalent to the formula when n is 1. Then on the left-hand side, I get. So if this formula is true, then this last line must be automatically true. H of v of x e to the minus v of x. So actually, the many-to-one formula itself, okay, I always assumed, so I forgot to say this, I work always under the assumption capital star, the assumption star. So if I only care about the formula itself, I only need the first part of the assumption. That's all I need. But the second part of the assumption tells me that in particular, the new random walk is mean 0. And that's very important in the sense that, okay, we have a random walk, but which is mean 0. And that's something very enjoyable. Okay, so these were more or less a very short summary of what we saw before the break. And I think we already started prove some quantitative theorem. So for example, under the assumption star plus some integrability condition, which I really don't want to trouble you because they are really not very interesting. Nobody cares about these integrability conditions. And this implies that if I look at the minimum position, we know that the minimum position goes to infinity, but it turns out that we even know how they go to infinity. They go to infinity like logarithm. Asymptotically, they go to infinity like 3/2 times log n. Okay, yeah. So if I want to prove convergence in probability, actually there are two parts. I need to prove that it's at least 3/2. Well, at least 3/2 minus epsilon, and it's at most 3/2 plus epsilon. So I fix whatever epsilon, I want to prove that the probability that the minimum is smaller than 3/2 minus epsilon times log n. I want to prove that this guy goes to 0. And where is the probability that the same quantity is smaller than or equal to 3/2 plus epsilon times log n? I want to prove that this guy goes to 1. So the two convergence together will give me the statement of the theorem. Okay, so the first one I'll call it 1, the second one I'll call it 2. Yes. Last time actually we proved the first part, but I prefer to remind you how we did it. So let me briefly remind you how we did it last time for the first part. I think I'm going to. So for the first part, if I fix a constant capital K, I fix a constant A strictly between 0 and 3/2. If I count the number of particles in the nth generation, such that the branching random walk at this particle is smaller than a log n, whereas all the ancestors is at least minus k. So for everybody, from the beginning until the very end. And it turns out that Zn is very small. It's very easy to prove that it goes to 0 in L1. So if I take the expected value of this guy, then I can use the magnitude-1 formula. With the g here is the indicator function that the last component is smaller than this one, whereas for all the components should be greater than minus k. Yes. So the magnitude-1 formula tells me that this is expected value of E of Sn, indicator function of the same thing. So Sn is smaller than a log n. And all the Si should be greater than or minus k. So this is magnitude-1 and nothing else. And then I realized that on the set that Sn is smaller than a log n, so the density actually is exponential to Sn, is smaller than or equal to n to the a. So everything is smaller than or equal to n to the a. Expected value of the indicator function now it's just a probability. So the probability that Sn is smaller than a log n, and moreover Si is greater than minus k. I remind you that S is a mean zero random walk, which I guess in Russia you prefer to call it sum of ID random variables, but okay, it's the same thing. And moreover, I think you probably know more than I do about sums of ID random variables. So this is the kind of things we regularly need to handle when studying branching random walks. We regularly need to handle things concerning sums of independent random variables. And it turns out that for this one, the probability is more or less n to the minus 3/2. Actually, it's n to the minus 3/2 plus a small o of 1. N to the small o of 1, it comes from the size of these logs. So the logs is not exactly constant, but actually I only care about the power of n, so it's all right. So this immediately allows me to see that everything goes to 0 because a is supposed to be strictly smaller than 3/2. Yes, so here I have n to the a, here I have n to the minus 3/2. So the product go to 0. So the expected value go to 0. It means that Zn is non-negative. So it means that Zn actually is goes to 0 in L1.
So you use this minimal constant.
Yes, yes, I do.
So that you may assume k to be fixed.
Yes, k is a fixed constant which can be as big as possible. Oops. So I have proved that Zn go to 0 in L1, so in particular in probability. Yes. And now I claim that the second part actually I can remove it because of this last piece. I know that everyone goes to infinity. Yes, so it doesn't cost me anything to assume that along the line is greater than or equal to minus k because I can take k as large as possible. So I fix epsilon, then I can choose k sufficiently large such that this happens with probability at least 1 minus epsilon. Yes, so this is sufficient. So if I remove this, it means that I cannot have even one particle in the nth generation such that the value is smaller than a log n. It means that everybody, the value is greater than a log n. And a can be as close to 3/2 as possible. So that gives me the first part. So here I use this fact. Oops. So I use the fact that the minimum go to infinity. Okay, in probability that's sufficient for me. So that's exactly where we stopped last time. Yes, so let me make a simple observation. In that at the beginning this is not, okay, it's a simple and clean proof. There is nothing very special. But at the beginning, when first I tried to prove such a thing, it was not clear why I should do this. So an observation is that probably it's more natural, instead of counting the number of particles in the nth generation such that all this is true. Probably it's more natural to count only the number of particles in the nth generation such that the value is greater than, smaller than a log n. And I want to say that this is impossible if A is roughly 3/2. Well, if A is 3/2 minus epsilon. I want to say that this is roughly 0. I want to prove that there is no particle such that this is true. Of course, I can do exactly the same thing, so I put it here. I can try to prove that it goes to 0 in L1, so I compute the first moment. So magnitude 1 tells me that this is the same indicator function that, oops, maybe I should write it downstairs. The magnitude 1 tells me that this is the same indicator function that Sn is smaller than or equal to A log n with the density function exponential to A Sn. It's exactly the same argument, except that I don't have this second piece, right? And I want to show that this goes to 0, right? It turns out that this is smaller, well, actually it's equal to n to the A minus 1/2 plus small o of 1. So far these actually are identities. So if you want this guy go to 0, then you need to assume that A is strictly smaller than 1/2, not 3/2. So if you do this kind of argument, what you will prove is that the minimum is at least 1/2 times log n, not 3/2. So the fact that you add this additional piece, somehow it makes this effective value decrease more or less dramatically. And we know that we can add this for free because we know in advance, we know a priori that everybody goes to infinity. So it costs me nothing to assume, to ask everybody to be greater than minus k. So it's a simple technique, but I mean, it's appreciable because it helps you, right? So actually, these last lines, these were the first lines I wrote at the beginning, and then I claimed that, okay, I have a lower bound which is 1/2 times log n for the minimum position. But it turns out that that was not sufficient. It was not optimal. Okay. So now you see what happens with the first part. The second part is exactly using exactly the same ideas. So now let me try to prove that the minimum position is at most 3/2 or plus epsilon log n. Again, I'm going to, well, I call it again Zn, but this Zn is different from the previous one. I count the number of particles such that it is smaller than 3/2 plus epsilon this times. And I know that I can add for free, it doesn't cost me very much. I asked everybody to be above minus k. Okay. So in the first part, I proved that the expected value was sufficiently small. It goes to 0, so I already knew that Zn go to 0. This time I want to have at least some particles inside. So now I want Zn to be at least 1. Yes? So this time I want a lower bound of Zn, not so I want to show that this probability, Zn is integer valued. So saying it's at least 1 or is strictly positive is identical. I want to show that this is greater than equal to something. Yes? So a usual way, this has nothing to do with the branching process or whatever. I claim that I can use this one. This is simply Cauchy-Schwarz. Cauchy-Schwarz say that you look at the square of the expected value, then it's smaller than the product of two, because in the expected value, you can put indicator function without costing you anything. Right. Okay. So I want to show that this ratio is greater than or equal to something. So we want For the moment, it's not clear whether it's going to work. I want to prove that the numerator is greater than something which is sufficiently good, and the denominator is smaller than something which is sufficiently small. Yes? So that's a generic proof without using anything particular of branching process. Very unfortunately, it's not going to work like that. This guy is too large. This guy is too large. The first moment is like the previous one. It behaves exactly like what you imagine. Unfortunately, the second moment is too large. It means that the choice of Zn was not very clever. We need to do something better. We need to do something better because somehow in this thing, it was sufficient for the first part. When we computed the first moment, it was all right. But somehow there are some events or part of the event gives you big values of second moment. The event is of very small probability. It doesn't give you much weight to the first moment, but suddenly they give you many weights to the second moment. So we need to remove these useless events. It means that I'm not going to look at this Zn. So this is not what I'm going to take. I need to take a subset of this one. I need to put it a little bit smaller so that the second moment will be sufficiently small. Yes? Here is what I want to do. Let's look at the branching random walk. Now we know that if we wait a long time, that everybody will. Yes?
Still 10 minutes.
10. Okay. We want to I think usually we stop at 4-5, right?
Yes,
okay. Okay. Maybe I can finish this one and then. I look at what I really want is the first part. I want to count the number of particles such that their positions are below this 3/2 times log n. Yes, the rest I don't care at all. Okay, so this is essential. I put it here. 3/2 plus epsilon times log n. So I have at the end it's like that, and then of course I draw like continuous thing, but everything is discrete, of course. Okay. Oops. So I want to count the number of particles that are below this level at n. Yes, and it turns out that I can allow myself to ask a little bit more. So this, look at it. I count the number of particles below this level at time n. And I allow myself to ask something similar, such that the whole trajectory is above this level. This level is, the height is k. Capital K is a very big constant. Okay, so let me write it here. I count Zn number of particles in the nth generation such that the position is smaller than an. So an, I'll write it here. An is 3/2 plus epsilon times log n. It's it's a little bit long to write 3/2 plus epsilon times log n. So I give it a name an. And moreover, so this is really the part which interests me. But unfortunately, itself alone, it gives me even too big first moments, not talking about second moment. So I need to cut off a few things which I'm not interested in. So moreover, I ask everybody for OI from the beginning until the end, I want everybody to be above this slope when I get down of height capital K. So this is greater than or equal to, so the slope is an over n, if I'm not wrong, so times I minus k. That's it. So I count the number of particles such that the value is indeed below 3/2 times log n. And moreover, I don't want it to be too low at the beginning, because that's not likely to happen actually. But unfortunately, if I don't remove this part actually is a very small probability, but it gives you very big second moments. So that's why I want to exclude such situation, which actually I'm not interested in at all. Yes, and we are going to see after the break that now it's going to work. So the first moments, there's nothing very special. You can do exactly as in the previous case. So now we need to show that with this added condition, then the second moment is going to be relatively small. We are going to see that after the break. Okay, so before the break, we saw where the problem was. Our second moments were too big. So once we saw the problem, we found a way to deal with the problem. We realized that, okay, we need not to take the whole event, but only as a sub-event which is of interest to us, and we were hoping that this sub-event would give us relatively small second moment, and we are going to see it will be the case. So now we decided that we count the number of particles in the nth generation. Not only the terminal value is below this 3/2 plus epsilon times log n, which I'll call an, and moreover, everything from beginning until time n, everything is above the second red line. Okay, and this will help us make the second moment smaller. Okay, so I want to have an upper bound for the second moment. So I remind you that the aim is to have a lower bound for the probability that Zn is at least 1. So the first moment is just magnitude 1, nothing very special. So I want to make this denominator as small as possible. So let me compute the second moment. So I want to have an upper bound. So in principle, I want to know whether this is smaller than the sum. This is exactly what I wrote here. Okay, so let's start now. Second moment, so it means that Z is a sum. So second moment actually is a double sum over each pair of vertices x and y in the nth generation, such that both x and y satisfy the same condition. So the first possibility is that x and y are identical. Why not? Then it's just the first moment, right? So the special case, x and y are identical, gives me just the first situation. And then I need to sum over, it's a double sum, over the pair x and y, and they are different now on the nth generation, such that, okay, the indicate function should be here, but I don't have enough space. The indicate function for both x and y, it means that for both x and y, the terminal value is smaller than or equal to an. And for both, for both their history, Vx of xi, v of yi, they are, everybody is above the line of the same slope, but, oh sorry, an over n times I minus k. And oops. So the writing is horrible, but the idea is trivial, right? Okay. The first part, I mean, I don't care at all because the kind of first moment we already computed even before the celebration of the armistice. So now let me look. Now I need to sum over a pair of different vertices in the nth generation. So maybe I should write it here. I have a pair of different vertices x and y in the nth generation. So this is the beginning, this is level 0, and this is the nth n. And I know that I'm trying to draw things in the genealogy tree, right? So this is the root. These are two vertices in the nth generation which are different. So somewhere there is how would you say, the youngest common ancestor for them. I call it Z. It means that the story from the beginning, the roots 0 until Z, everything is common for x and y. But starting from Z, then you have different things. And so Z, it could be anywhere between 0 and n, but n is excluded because x and y are different. Yes, so I call it J. So J is between 0 and n minus 1. Yes? By this difference, so sum over J from 0 to n minus 1. Take the expectation sum over vertex Z in the jth generation. Okay. If I call Z the youngest common ancestor of x and y, it means that after Z, things are different. It means that Z have two different childs. This one and this one. These are different. And this child will at the end have x in the descendants, whereas the other one will at the end will have y in the descendants. Yes? So this, by our notation, is what usually we call xj plus 1, because this is in the generation j plus 1, right? So this usually we write it as xj plus 1, whereas the other one is usually we write it as y indexed by j plus 1, right? That's the usual notation. Yes. Okay, so let me sum over the different pairs xj plus 1 and yj plus 1. And at the end, I sum over the pair xy. Okay, so it looks horrible because I have a triple sum, yes? But each sum actually will be very easy. Okay, I need to just copy the same indicator function, yes? But the indicator function, actually, I prefer to write it, to cut it in two pieces. The first piece is from 0 to jth generation because it only concerns the parts from this beginning until Z, and that's a common story for everybody. Yeah? So for that part, I know that V of Zi should be always above the slope n over n times I minus k. So this is for all I from 1 to j. And this guy has nothing to do with what happens afterwards. So actually, my writing was not very careful. I really should put, this indicator function there because this is the sum for Z, but not for what happens afterwards. It's a common thing, yes? So what happens afterwards will be in the second indicator function. Now I write everything starting from j plus 1 until n, yes? So the same story. So V of y of j plus, I'll call it L is greater than an over n L minus k, and V of, this is XL and YL, excuse me, YL, exactly the same thing for all L starting from j plus 1 to n. Yes.
Where is the condition that V z of y less or equal than a?
Good point. I haven't written it yet, which I should add now. Yes. And moreover, V of x, v of y should be both smaller than an. Now I think I have included everybody, yes? So actually, the indicator function becomes bigger, but actually from mathematical point of view, things becomes cleaner, because I know what happens for this piece, what happens for the other piece. Yes, okay, so now I need to just to repeat, but I think everybody already see what it is. So this, the pair xj plus 1 minus yj plus 1, this is distinct children of z. They should be different, yes, because they separate from them. And then here is the sum actually of x, which is in the descendant of xj plus 1 in the nth generation, and the y is in the descendants of yj plus 1 in generation n. They are certainly different because xj plus 1 and yj plus 1 are different. So they have different ancestors here. These are brothers, actually. So of course, the descendants are all different. Yes? Okay. So now I have a horrible, well, which apparently horrible expression, but actually each expression is very easy to handle. So this will be, I think I will write it here, and that's it. Oops. I don't need this picture anymore. So it turns out that I have a huge expectation to manage, but the easiest I'll do it in different steps. So first I'll look at the double sum for the pair xj plus 1 j plus 1 yj plus 1 and double sum xy everything, and I look conditioned upon what happens until the jth generation. So everything, which means that these things, they are measurable until generation j, because they only concern the first common part. Yes, whereas starting from generation j plus 1, everything will be completely new. Yes, and moreover, since they separate, so actually I have two independent pieces. So actually this is the square of something. Yes, and here I need to use, unfortunately I need to erase it. Here I will use what I assume here, because I know that at the value of v at position j, I know that it cannot be very small. It's above something. Yes. So I start from something relatively high. Then, okay, it's very hard for me well, it gives me a small probability to have a small terminal value. So that's why I added this additional condition, just to make sure that the position of branch random walk at position at vertex z is relatively large. It's at least this high. Well, the exact position is not very important, but I have some lower bounds to say that it's very high. Okay. Anyway, so this part actually is the square of each part. You do it just by magnitude 1 and nothing else. Because if you condition upon the value of Vz, then it's about something, the sum of everything along the whole passes. That's exactly what tells me magnitude 1 and nothing else. Yes. So assume that you are able to do that, and then you are going to see again sum over z in the jth generation. And this involves what happens from the beginning until z, and also something here you'll get a function of v of z, a complicated function but explicit function. So that's again magnitude 1.
You also must count the number of pairs.
Sorry?
You also must count the number of pairs.
Here there is no pairs at all. Here I have the square. Yeah, here I have the square of something.
You have the square of something for each pair xj plus 1, yj plus 1, right?
Oh, okay, yes. When I say that in my theorem, very unfortunately, I already erased the statement. I told you that there are some integrability conditions. Yes, and it's part of the integrability conditions. I need to say that you don't have too many children. It's not true. Actually, my condition is not that at all. My condition is that you don't have too many children whose positions are low, because I'm not afraid of having many children if their positions are very high, because they are not likely to give influence on the minimal position. I care about the minimal position. What I'm afraid of is to have too many children and having low positions. So I want to exclude this. Yes. So I have an integrability condition which guarantees me that actually my children are not like that. So I have some integrability condition, and that will allow me to deal with this part. Okay, I don't want to get into the details of that because, okay, for one, they are not very nice. Each time I try to do it by myself, there is a fair chance that I make a mistake. And for two, mathematically speaking, they are not. There is nothing very special. All you need to do is to be very careful.
For example, if you just require that the second moment of number of children exists, this would be fine.
Yes, actually, I need a lot.
You want to find something more elaborated, but if this expectation of number of pairs is finite, then there is nothing to.
Yes, we believe that the naked number of children is not what you need to know.
So in your model, the position of children doesn't depend on the position of parents, yes?
No. The increment doesn't. But of course, you are born in the place where your parents die. So it's your increment plus the position of your parents. So in this sense, your parents' position are important because that's where you were born. But your own displacement has nothing to do with your birthplace. It's exactly like some of IID random variables. Sn plus 1 certainly depends on Sn, but the increment doesn't depend on Xn. Yeah. Okay. So, okay, I prefer not to get into detail. It's just like, how would you say, when students do the first exercise on Borel-Contero lemma, they find it very complete. How do you know which part of the lemma you need to apply and so on? But once they do a dozen of exercises, then they realize that, okay, it's always like this. I mean, there is a kind of routine. Here there is something very similar. When you do it for the first time, you get the impression that, oh, well, it looks very complicated because you need to deal with this with you. But then you realize that it's always the same routine. I mean, you don't need to have any new idea. You follow exactly the same lines. Okay, but so I assume that you are able to deal with this triple sum, the expected value of the triple sum. At least at the end, you need to still to sum. Okay, there is no more random variables. Everything is deterministic. You need to do it by yourself. Okay. And that's more or less the end of the story. So I write the conclusion. At the end, what you get is what you expect. That's the second moment is bounded by a constant multiple of the square of the first moment. So if I use Cauchy-Schwarz inequality, I get that with the positive with probability greater than a constant that there will be some 1. So if there is some 1, it means that the minimum value is smaller than an. An is 3/2 plus epsilon times log n. Yes? So I'm almost home. Oops. So at the end, what I get is with the probability at least 1 over capital C, the minimum value at the nth generation is at most 3/2 plus epsilon times log n. It's very nice, but my claim in the second part of the theorem is that the probability is 1, not just with a positive probability. Okay? So there is one last thing missing, but this is also routine, because on the tree, it's very well known that if something can happen with not too small probability, then it's going to happen with the probability 1. That's related to the tree structure. Okay, here is a very simple argument. So it's an argument which you use almost everywhere, but I write the arguments only in the case when capital N is non-random, is a deterministic, but you are going to see that if it's random, it's exactly the same argument. So capital N is the number of children you have each time. So assume that it's just 3, it doesn't move at all, yes? For the moment, I prove that the probability is at least greater than a given very small constant. And now I want to say that this probability actually is greater than or equal to 1 minus, okay, I should not use the same epsilon, let's say 1 minus eta, yes? For eta, any given constant, I want to prove this. For any given eta, I want to prove that this is true for all sufficiently large n, yes? So what I'm going to do is to fix, A is fixed such that 1 minus 1 over C to the power capital N to the K is, which is smaller than eta. This is, I'm certainly able to choose such a K because this go to infinite, whereas 1 minus 1 over C is strictly smaller than 1. So for K sufficiently large, I know this is true. So I fix K. K is fixed. I don't touch it anymore. Yes? And then I look at what happens. So this is a very elementary argument. It has almost nothing to do with the branch random walk. It's related to the tree structure. And I'm not surprised if you have already used by yourself this kind of arguments in your own problems. So if I look at the probability that the minimum position in the generation n plus k is, I want to look at the position probability that this is greater than the maximum position at generation k plus an. An is 3/2 plus epsilon times log n. Okay, so which means that I look at the generation k plus n. So this is generation n plus k, this is generation k, this is generation 0. Yes? So if at the generation n plus k, the minimum value is already greater than any any position in the generation n plus k is greater than any position in the generation k plus an, then certainly this would be true that if I look at this subtree rooted at this vertex at the k generation, then in this subtree, the minimum position is greater than an. Yes? So this will give smaller than the minimum position in the nth generation of V is greater than AN. Well, actually, this V is not the original branching random walk, but rather the branching random walk associated with this subtree, right? But it's the same probability. And of course, if I consider this subtree, again, the same inequality is still true, yes? So for this subtree, the same event is still true. And these are independent things. So all I need to do is just to count the number of subtrees at generation k, which by definition is capital N to the k, because I assume that capital N is a constant. Yes? So this is smaller than this guy to the capital N to the k. Yes? Because all these subtrees, of course, are independent. That's the definition of my model. Yes? And each of the probability, according to what we have already proved, this is what we call the AN, right? So this event is greater than 1 over c. And the event I wrote here is 1 minus the probability. So this is smaller than or equal to 1 minus 1 over c. Yes? Yes, OK. And that's finished. That's 1 smaller than 1 over 1 minus c to the n to the power k. And you see that according to the choice of k, this is smaller than it. Which means that this is not going to happen. Actually, the inequality should be the other way around. And the k, nobody cares. K is a constant. Nobody cares, yes? N go to infinity. An is 3/2 plus n log n. There is no difference between n and n plus k, yes? And that's exactly what's written for 2. So that's exactly what we proved. Yes? Now it's the end of the story. Yes. So this last piece actually is completely elementary. It has nothing to do with the branching random walk. OK, so you see that we didn't use anything very sophisticated except this many-to-one formula. So I hope I have convinced you that many-to-one formula is really what you need to know if you want to study branch random walk. So I told you that this is the only quantitative result which I personally know and which I use quite regularly. OK. So we have proved that, so under assumption star, the minimum position divided by log n goes in probability to 3/2. Yeah. It turns out that it's possible to do a lot better, but that will be very hard to prove. And I believe this is probably the most important result in the last decade or in the last 20 years of the study of branching random walk. So it says that actually we can say a lot more. Under the assumption star plus exactly the same integrability conditions, which I'm not going to mention. And if the law of the, which I call capital L. So I remind you that capital L is the random vector xi1, xi2, xn, right? It's the random vector which determines the law of the branch random walk. Yes? If the law of this random vector is non-lattice, it means that you cannot find any pair of real values A and B such that all the components of the random vector takes value in A plus BZ. Yes? You don't live in a very small world. So for example, this excludes the Bernoulli case. For Bernoulli, it takes only 2 values, 0 and 1. Yes? So if this is not it's not lattice valued because otherwise there is a problem. Then the minimum position, in the nth generation, we prove that divided by log n, it converges in probability to 3/2. Actually, even minus 3/2 log n itself converges weakly to something. If it converges weakly to something, of course, divided by log n, it converges weakly to 0. It means that it converges in probability to 0. And that will give the proof, the theorem we have just proved. So the Idicon theorem says that this itself converges weakly to something. So look at the probability that this is greater than, let's say, I don't know, maybe call it alpha. So for any alpha, real number alpha, it converges when n goes to infinity. It converges to the expected value of exponential to the minus a constant, whoops, c times d infinite e to the alpha. Okay, let me say one word about the statement. So I copied the same expression. I guess it's written too small. So the limit, I write it here. Expect the value of e to the minus a constant times d infinite times e to the alpha. This is the tail distribution of the so-called Gombel distribution if you don't have c and d infinite. If it's just e to the minus e to the alpha, this is exactly the tail distribution of the Gombel distribution. So this really is a Gombel, but you have a random shift which is log of c times d infinite, right? So here, c is a constant, finite and strictly positive constant. And d is the almost sure limit of the derivative martingale. Now you see that the derivative martingale is very important. And under this integrability condition, which I haven't given you the exact statement, it's possible to check that the limit is strictly positive almost surely. Yeah. So everything is good. We have already seen something very similar, but for branching Brownian motion, and that was Brahms. Yes. So remark. So for branching Brownian motion, this is already known by Bramson for quite a long time. So I think for about 30 years, everybody believed that there should be such a theorem, but nobody was able to prove it. So it was a big breakthrough that someone actually managed to give such a proof. So Bramson already proved for branching Brownian motion, and I told you that this condition is important, the condition of non-lattice, because if it's lattice, then it's quite possible that it doesn't converge. Somehow it turns around, but without converging to, you have this cyclic phenomenon. It's possible. So there is some, I think it's Bramson, Dean, a very young mathematician, and Zaituni. So they, I'm not sure whether the paper is already published. They deal with this lattice case. So they are able to deal with the case when this cyclic story. Okay.
And in the lattice case, the limit will be the same?
There is no limit.
No limit.
Yeah, because you do, yeah. Misha certainly can tell you more because he studied some lattice case quite some time ago.
Many years ago, I considered the special case of Bernoulli random variable when we have.
You have
there is, I think, no logarithm but iterated logarithm in centration, and then there is cycle in the space of distributions, and the distribution of minimum walks along the whole cycle. So that in the space of distribution we have not one single limit, but infinite, one-dimensional set of limiting distributions. But they did it for general.
Yes, yes. And moreover, you don't divide by anything. The point here is that there's no normalization. You look at just something which go to infinity, but you subtract something and you prove.
This is because you apply star.
Yes, yes. Yeah, oh, sure. Yeah. Sure, yes, yes.
The linear growth is hidden.
Yes, yes, of course. Sure, yes. I have 3 minutes to tell you a story, right? Okay. So, a little bit more. So we saw that the minimal position at time n is 3 halves log n, right? So a natural question is it always that small in the past? For example, when at time n over 2, at the branching random walk, is it also something like log n or maybe greater than that? Okay. So if I look at, so I'll make a picture. We know that at time n, so the minimum will, this guy I know that is roughly speaking 3 halves log n. So if I look at the whole path, the whole history of this guy, is it always that small? And the answer, well, I guess you probably can guess the answer. Actually, it's no. So if n star is something in the nth generation, so which in our notation that the absolute value is, so this is something, a vertex in the nth generation, and oops, excuse me, such that, I think I did something, oh, okay, first down, such that it reached the minimum position. If there is one, then you don't have any other choice. If there are several, then you just pick up at random one of them. If there are several vertices reaching the minimum position, yes? And then I write xni star, the ancestor of x star n at generation I. So for I between 0 and n. Yes? So this is xnn, and this is x, well, the vertex is xni. Yes? Okay, so the question is, I'm asking is, what can I say for this sequence, the position of the whole red path? Yes? That's a very natural question. And here is what's proved recently by Xin Chen. I think that was 2 years ago. So she proved that you use the same assumption plus exactly the same integrability condition, which I never write down. It turns out that basically it can be very big. It's not always log. Rather, log is an exception. So she proved that if you look at v of x star n indexed by the integer part of nt, and she looked at this as a process of t in the one, just like in Donskoy's theorem. She has a Donskoy type invariance principle divided by sigma times square root of n. I'm going to tell you what sigma is. And this converges weakly. Well, okay, this is discrete. If you want, you can do linear interpolation so that everything will be continuous. So, it converges to a very nice random process, which I called ET. So here, sigma square is defined as expected value of the sum of everybody in the first generation, Vx to the square, e to the minus v of x. Actually, in our notation, this is the variance of the new random walk, which appears on the right-hand side of the magnitude formula. So it's not a surprise that, okay, the variance plays some role, right? So it's this integrability condition, which I don't write, ensures that this random walk Sn does have a finite variance. Okay, and so I need to say what E is. E is the so-called normalized Brownian excursion. I don't think I want I need to give you the exact formal definition of the normalized Brownian excursion. Probably Andre here will be able to tell you a lot more about this process. Informally, you take a Brownian motion over zero from 0 to 1. If you condition that at time 1 you are 0, that's what's called a Brownian bridge, standard Brownian bridge, right? It starts from 0, it ends up at 0. Yes, and then now you force your Brownian bridge to stay non-negative. Then it becomes a normalized Brownian excursion because it's not 0, and moreover, it's always positive. Whereas the Brownian bridge can come back as often as he wants to 0. If you don't want it to come back to 0, then it's positive. At the end, it doesn't have any other choice because you force it to come back. And that's a so-called Brownian excursion. And that's exactly what happens with this guy. We know that it cannot be negative afterwards because it goes to infinity. So you look at, well, it's not a proof at all, but if you look at the new random walk Sn, we know it's above minus k. So somehow it's mean zero random walk, and you want it to be positive. There is no difference between positive and above minus k, right? And at the end, we know that it comes back to 3/2 log n. But you divide it by square root of n. So 3/2 log n divided by square root of n is basically it's 0. So you have more or less a mean zero random walk, starting from 0, and you force it to come back to 0 at the end. And moreover, you don't want it to be negative. So what else but the Brownian, normalized Brownian excursion? It's not a proof at all, but I hope it's not a big surprise. So if we admit this proof, this result, then in particular, we know that in the middle, the typical value is square root of n, not log n. Log n is only at the end, it comes to be very slow, but typically in the middle, it's square root of n, not log n at all.